Ta-da! Okay. Is this working? All right. Week 2 Friday. Week 2 Friday. Okay. Oh, so just a tiny bit of housekeeping. This coming Monday, I got something going on in the morning, so I'm gonna reschedule our lecture to 6 p.m. via Zoom. Okay, and again, if you can come, and if not, I'll record it, and that'll be that. Okay, so that's that. So I mean, I don't know if this is like your earliest class or whatever, but if you want, you can sleep in on Monday. If I don't know what time everybody wakes up, right? Some of you like wake up at 6:30 a.m. every day, no matter what, and then some, it's like a struggle to get up before noon. But I don't know. I mean, there was one quarter during the pandemic remote school, where like all of my classes were in the afternoon. And it was a struggle just to get up before like 11. I was like, I had no motivation. I'm not laughing about depression here, but just, yeah, it was rough times sometimes, right? Okay. Well, anyway, let's talk about today's lecture. So we are going to cover this topic called regularization. And this is a technique that we use in machine learning to kind of reduce overfitting, right? So overfitting is the idea that, you have your training data, you have the data that you are using to train your model to figure out what is the slope and the intercept or whatever model parameters, those coefficients, what you're trying to do. And if you overfit your data, that means you have done a very good job of coming up with the exact numbers needed to predict the values that exist in your training data. But then when you see new data, it does a bad job of predicting, right? So for example, you might want to be able to predict, people's test scores or something. And maybe you ask them, what's your GPA in the other classes? How many hours of study do you do each week? And what were your homework scores and things like that? But then it's also possible you've gathered a whole bunch of other information, like what color t-shirt do you wear and what size shoe do you wear and things like that, right? And perhaps in your training data, it turns out that everybody who wore a gray colored t-shirt and wore a size 8.5 shoe happened to score a 95 on the exam. And so you go, oh, look at that. And with the machine learning, it doesn't know, right? A human would say, well, that's ridiculous. We're not going to model this, right? But a machine learning doesn't know this. It just says, oh, look, I found a pattern. Let's dial this in. And so the algorithm might say, oh, if we see somebody with a gray shirt and 8.5 shoe, they're going to score 95. And they put that in the model, okay? That would be overfitting. Because what happens is new data comes in, and this was, as humans, we recognize that was just a coincidence. That was just a coincidence that, you had 3 people that day that happened to be wearing gray shirts and happened to have 8.5 shoes, and they happened to score a 95 in the exam. We recognize that's got to just be a coincidence. And so when new data comes in, and there's somebody wearing a gray shirt and an 8.5 size shoe, the overfit model will say, oh, 95. It's got to be a 95. And then it turns out, oh no, it wasn't a 95. It was a 67 or something like that, right? And why is that? It's because those variables actually have nothing to do with the test score, right? And it's just, if you overfit your data, it just means you found some weird peculiarity that happened to exist in your training data. Is not something that actually exists in real life, but you end up fitting that, okay? And so cross-validation is one way to try to avoid this. Cross-validation says, hey, you know what? Let's shuffle up our data, okay? Let's have a training set and a validation set, and And hopefully that avoids some of these issues where, you know, you're not going to overfit some of the pieces of information, right? So that's cross-validation. It kind of cuts things, so you have data to train on, and you have kind of like a test run on your validation set, things like that. The other method, or the method we're going to look at today, is called regularization, right? And this is another way that helps us avoid overfitting. And what it does is it modifies how we calculate the loss function. And in particular, it will add a penalty to the loss function if your model is overly complicated, okay? So it might say, you know what, this model that takes into account the t-shirt size and, t-shirt color and shoe size and whatever it is, you know, now you've got like 70 different variables that we're looking at. That's just too complicated, and I don't think all 70 of these variables are quite useful. Let's try to parse it down to, I don't know, 4 variables that are more useful for predicting, okay? So, you know, what we've been looking at so far has been the mean squared error or the total squared error, depending on whether you're including this 1 over n constant, right? So you've got the actual value t minus the predicted value, which is currently x times w, and we have t minus xw transpose times t minus xw, okay? And so if this is our loss function, the best model is the one that minimizes the mean squared error. And if we're guided only by this principle, we can end up selecting an overly complicated model, because we see that, you know, if we keep adding variables to x and we keep adding parameters to estimate, the w parameters to estimate, you know, we might go for the 17th degree polynomial or something like that, right? If we're guided only by the mean squared error, the one that kind of minimizes the mean squared error is going to tend to overfit, okay? Because generally, more complicated models will have a lower mean squared error than a simpler model, okay? And what we're going to do is we're going to modify this loss function. And in the homework, your very first problem, you modified, I think the first 2, you were doing weighted least squares, right? And so what that did is it modified the least squares function by including this weight matrix A, right? And that puts a weight on each of the different points. And what that ends up doing is when you change the way the loss function works, it's going to end up changing the coefficients that get calculated. And so in weighted least squares, you say, well, you know, these observations are really important. We don't want to have big residuals on these observations. And so it ends up picking a slope and an intercept that's going to fit the heavily weighted observations, and even if it means having much bigger residuals for the other observations, okay? And I think we saw that in our homework, if we've gotten that far in the homework, which hopefully we at least started looking at that, right? So that's one example of modifying the loss function, and we can see the effect of modifying the loss function results in different slope and intercept coefficients. Okay. This time, for regularization, what we're going to do is we modify the loss function by including a penalty term for the model's complexity. Okay, so here I call my loss function L prime, and all it is we take the ordinary least squares loss function L. Okay, so that this part's going to be the same. All right, so we have that plus, and then we just throw in this lambda times complexity. Okay, lambda times complexity. And so we're going to have some way to measure complexity. And we're going to say, basically, if it's more complicated, the total loss function, this L prime, is going to get bigger. Okay, so remember, we want to minimize this. So we want to minimize this, and the way we're going to minimize this is we're going to either we've got to shrink this, but we don't want to shrink this so much if it's going to increase the complexity, right? So, we don't want the complexity to go up, because if this gets too big, then this will go up. But if we don't do a good job, if we just work on shrinking complexity only, then this thing might be big as well, right? So these are kind of different priorities, and so lambda is kind of a weight between which of these priorities is more important, right? And so the result of this is we're going to end up getting coefficients that are going to be different from the OLS coefficients. All right, and so this is my analogy to real life, in that a lot of times when you're looking for something, there's different kind of criteria that you have in mind, and they might both be, you might have several things that are important to you, but you might try to choose one that is more or less important or something like that. And so here is, so let's say, after you graduate, you get a job, and then you have to find a place to live, right? So this is, maybe you can work from home and live with your parents, and that would be like, well, if you get along with your parents, you can save a lot of money, and you can work from home, and you don't have to commute, and that's like the dream, right? But there's also a good chance that you work somewhere, and you have to, you move somewhere, and you have to find an apartment and things like that, and so you're looking for an apartment. All right, so there's lots of things to consider when searching for an apartment, but just for simplicity, let's say we're going to look at just the cost of the apartment and the commute time, okay? Obviously there's more, right? Like, are there cockroaches or something, right? Like those are things that factor in, and you might say, well, okay, but anyway. All right, so let's say one apartment costs $2,000 a month, and the commute to work is 10 minutes, okay? And then another apartment costs $1,700 a month, but the commute to work is 40 minutes each way, all right? And so depending on who you are, one person might pick one over the other, right? And so if money is the only factor that matters, then the decision is easy. You just pick the apartment that's a lower cost, and you can probably find an apartment even cheaper than $1,700 that might even be farther away or something like that. Well, who knows, right? But if money is the only factor, if there's only one priority in your life and it's money, then your decision making is easy. Just pick the cheapest one, right? But most people value their time, and the apartment that comes with lower rent comes with a different cost, like a penalty, right? And that's how much time you have to spend on your commute, right? And so if your personal time is very important to you, so like you have an active social life, or romantic partner or something, or maybe you just hate commuting, then you would weigh the penalty of the longer commute a lot heavier, right? And you would probably end up selecting the apartment that's closer to work, even if it costs more, okay? On the other hand, if you don't mind the commute, or if you don't have much to do outside of work or something, okay, then the penalty for having a big commute is greatly reduced, right? And you would pick the apartment with the lower rent. So kind of the true cost, the true thing that you have to think about in this simple example is you take the cost of the rent plus some mystery preference factor that will be different for each person times the commute penalty, right? And this is going to be different for each individual. Somebody might say, oh, I really hate commuting. The dream for me is living next door to the office. I can just walk right over there, and I'm willing to pay, extra $100 per month to make that happen. And then someone says, you know what? I like listening to my podcast. I like listening to audiobooks. Or I like driving in traffic. And they say, well, I'll live far away and save a bunch of money. And that's fine, right? And there's, of course, other things, right? Like, I'd rather just live at home and, save even more. I like living with my parents, and they cook dinner. So that's great, okay? That makes our model much more complicated. But so that's kind of what's happening, all right? Except here, we have the least squares regression, okay? So we're going to say, all right, we want to find the model that minimizes the squared residuals, but And we can reduce the squared residuals by adding more terms, by making it more complicated. But then somebody might say, well, you know what, I don't want a complicated model. I don't want a complicated model, right? Okay. So one thing to keep in mind, though, is we're optimizing a loss function. So this previous example, we're just comparing two apartments. It's kind of more like, when you're searching for an apartment, you got to kind of factor all of these things all in at the same time, right? So here we've modified the loss function. We're optimizing the loss function. And what we're going to do is we're going to find the best coefficients to use. And we're looking at the mean squared error, but we're also factoring in the penalty when we do this. All right, let me give you your first view quiz answer for today, which is, what is it? I gotta look this up here. It's B. B is your first view quiz answer. B. B as in bear. B. Okay. So we are going to do regularized least squares, all right? And what that means is part of it is least squares. This L term is the ordinary least squares, so mean squared error or total squared error. And then here we have lambda times the complexity, okay? Now here I just use the word complexity, but more generally, we have a regularization term, which is just some function R of the fitted function. Okay, so the model that we're fitting, that model that we're fitting F, we put it into another function R, which calculates whatever this number complexity is. Okay, now how do we measure the model's complexity? There's a few ways to do this. All right, and you can click the Wikipedia link that talks about regularized least squares, and you've got these different ways of measuring complexity. And that's what we have. Okay, now I have a prime here, and sometimes we think, oh, this is the derivative. This is not the derivative, okay? So don't get confused. This is not the derivative of L. This is L prime, indicating it is something related to L, but not exactly the same, okay? So that's like another notational thing that people do. They say this function is related to this other thing, but it's not exactly the same. Kind of like y and y hat. Here we have L and L prime, indicating that this is not, it's related to OLS because OLS loss function is L, but it's not exactly the same. So it's L prime. It's L plus this complexity thing. Okay, so one way we can measure a model's complexity is just how many terms are non-zero, okay? So model A fits a fourth order polynomial, and model B fits a fifth order polynomial. And in this example, we know the fifth order polynomial is more complicated, and we would have 6 weighting terms, right? The intercept, W1, W2, W3, W4, and W5, okay? And if we force W5 equal to 0, then that reduces it to a fourth order polynomial, W0, W1, W2, W3, W4, and the fifth one being 0. And so this is a simpler model, okay? So one way we can measure the complexity is to just count how many non-zero coefficients we have. How many non-zero coefficients is one way to measure complexity, right? And if you think about your vector W being this, all of the coefficients we have, W0, W1, W2, W3, W4, how many non-zero coefficients you have is known as the L0 norm, okay? The L0 norm, so you have like your L1 norm and your L2 norms, and I think, right, we remember this? So when we're talking about some vector W, how many non-zero terms are there? That would be your L0 norm. Okay. But trying to optimize this is really hard. Okay? So if we use the count of non-zero elements in some vector W, right? And we're using the L0 norm, so that is we're doing the norm of W, but the L0 norm, okay? and we say this is the function we want to optimize, right? So we have OLS plus this thing, okay? It's hard to optimize, okay? The loss function is not convex, and we have to consider all possible permutations in which of which elements in W are not zero, and when they are zero, and things like that. And if they are not zero, what value should they be? And as far as how many terms we have, or how many possibilities there are, it becomes really hard to do. Okay, so we don't generally attempt this. Okay, this is usually the most simplest and straightforward as far as like, oh, okay, that makes sense for a complexity thing. Okay, so what we can do is, instead of counting how many elements are non-zero, what we can do is we can take the absolute values of the elements in W, okay? And this would be your L1 norm, or your Manhattan distance norm, okay? So you say, well, let's just take the absolute values of each value in W. And this could serve as a measure of complexity in the model. So basically, non-zero values of W, so any element in W that are not zero will contribute to the penalty factor, and larger coefficients will contribute more to the penalty factor. And if a coefficient is near zero, then the variable if a coefficient in W is close to zero, say like 0.001 or something like that, it doesn't contribute very much to the penalty factor, okay? And so when we try to optimize this loss function, then, you know, what we're trying to do, we start off by trying to minimize the mean squared error, okay? But at a certain point, if we try to reduce the mean squared error, if it comes at increasing your coefficient W, okay, then the reduction in that mean squared error has to be greater than lambda times the growth of the coefficient W, okay? And this kind of strategy, this regularization, this is known as LASSO, okay? LASSO. You can read more about it there. Another way we can do regularization is called ridge regression. And here, rather than using the L1 norm, we use the L2 norm. Okay, so we take the elements in W and we square them. We take each W and we square them. So what this does is any values of W that are big, they get squared and they are heavily penalized. Whereas smaller values of W are penalized or penalized, but much less so. And this is known as ridge regression. Okay. And one effect here is that ridge regression ends up preferring values in W which are similar in size to each other. That's kind of a side effect there. Okay. Now, oftentimes, students will object and say, how is using the actual coefficient itself? Yeah, question. Yeah. I'm sorry. Okay, so you're asking about L0, L1, and L2 norms, and the question was? Yeah, you'd include the intercept, yeah. Or, well, I guess you could leave it out too. Well, anyway, but an objection is, why does the size of the coefficient actually matter? Why does the size of the coefficient? So that is, if two models have the same number of variables, aren't they equally complex? Okay, so this is kind of a, so if you have two models and they have the same number of variables, you might say, well, these are both equally complex. Why is the model more complicated if it has a bigger coefficient? Okay, if bigger coefficients mean more complexity, can't we just change the size of the unit and shrink the coefficients, right? So like rather than measuring in meters, we could change the measurement to be in I don't know, kilometers or something, and that would shrink the coefficient to be something smaller, all right? And then that would end up reducing complexity if we just change the unit size or something, right? Couldn't we do that? And these are valid points to bring up. And so I want to try to address these things and talk about why the size of the coefficient could be used as a measure of complexity, okay? So one thing is to kind of address this thing about unit size is that if you're going to use regularization, it's recommended to center and standardize your x variables, okay? Centering means adding or subtracting some kind of constant so that the mean of the column ends up being 0, okay? So that you're centering your vector, or you're centering your column of x values so that it has a mean of 0. And then standardizing would be multiplying those values by some kind of constant so that the standard deviation ends up being 1, okay? So multiplying by some positive constant so it ends up being having a standard deviation of 1. Another alternative is to scale all the variables so that they're scaled from 0 to 1, and that's useful if you just can't accept negative values or something like that, okay? So standardizing affects the concern that using different units will affect the size of the coefficients, right? So after standardizing, all variables will have a mean of 0 and variance of 1. Now, there are times where you don't want to standardize. Okay, usually this involves things like money, okay? Because, when we talk about unusual observations, we might say, oh, this is 2 standard deviations above the mean, or 1 standard deviation below the mean, or something like that, right? That's what standardizing does, okay? But when we talk about money, if we're talking about big quantities of money, we might say like plus or minus. It has to be like plus or minus $1 million. Like $1 million might only be like half the standard deviation or something. Okay, but if you standardize that, then a change of $1 million for one variable will count as like half a standard deviation. And then maybe in some other thing, if we're like talking about price per unit or something, a change of like 10 cents could be half a standard deviation or something like that. Okay, now from a business perspective, you probably, well, I guess it depends on the quantities involved and stuff, but you're generally concerned about the total cost and not just how many standard deviations and things we're looking at. So a lot of times, so for like money things, you might not want to standardize because the actual cost actually matters and things like that. Okay, but for a lot of other things, you will standardize the variables. That should address the concern about the using different units, okay? But still, we're asking, how does the size of the coefficient measure complexity? All right, so let's say we have 2 competing models for the same input matrix X. X has been centered and standardized. Both models have 4 X variables. Both models have the same coefficients for variables 1, 2, and 3, X1, X2, and X3. So we're having the same coefficient. The only difference between model A and model B is that model A has a big coefficient for X4. Let's say the coefficient for X4, W4, is 1, whereas model B has a small coefficient for X4. Let's say its coefficient is 0.01. Okay, so with the exception for the coefficient of X4, model A and model B are exactly the same. The only difference is that the 4th coefficient, W4, is 1 or it's 0.01. Okay, and I would argue, even though they both have 4 variables, X1, X2, X3, and X4, I argue that model B is less complicated than model A because model B has a smaller coefficient than model A. And you might say, I still don't get it, right? I still don't get it, or maybe this makes sense, okay? So here, what we have is when you have a tiny coefficient for a variable, what it means is that changes in that predictor variable will have little impact on the outcome variable, okay? So if we're looking at model A and model B, when x4 changes, variable x4, it affects model A a lot more than it affects the prediction for model B, right? So if we have these two models, and model A has coefficient 1, and model B has coefficient 0.01, a change in x4 barely affects model B, whereas the change in x4 affects model A. So if model B has a tiny coefficient for x4, it's basically placing less importance to the variable x4. And even though they both use variable x4, model B is kind of pretty much ignoring x4. Like, it factors it in, but it only factors it in a tiny bit, okay? And because it's pretty much almost ignoring x4, I would say it's the simpler model, okay? And here's my kind of silly analogy, is let's say you have two students. Both students are involved in a bunch of clubs on campus, okay? And one of them is like fully invested in all of their clubs, you know, maybe is like holds officer positions, has to attend all of these planning meetings and stuff, has a busy schedule. We'd say maybe lives a complex life, okay? Their life is full of all sorts of obligations, okay? The other student might be quote unquote involved in the same number of clubs, but just kind of marginally invested, doesn't really care so much, just shows up whenever they feel like it, skips meetings whenever they feel like it. I would say the second student's life is simpler and less complicated, okay? Do we agree kind of with that statement? So even though they're both involved in the same number of things on kind of paper, because one is like a lot more heavily invested than the other, they end up having something a little bit more complicated, okay? So I would argue that the weight placed on each of these predictor variables, especially after it's been standardized, can be used as a measure for how complex the model is. That is, if you have big coefficients, you're taking into account each of these variables a lot more, and if you have smaller coefficients, it means you don't really care so much about these variables as much, okay? So here's a very simple example, all right, to kind of illustrate how these regularization things work, okay? So x1 and x2 go 1, 2, 3, 4, right? And the true relationship between x1 and x2, the true t, is we're going to take 1.5 times x1 plus 1/2 times x2. So these are the values that we want to figure out. But I'm going to just add some random noise. And we want to model, we want to figure out what are the coefficients for x1 and x2. Okay? And so using LM, just taking each of these values and figuring this out, LM says the best parameters to use are 1.458 and 0.453, okay? So it's not exactly 1.5 and 0.5 because, you know, I added some random noise, and so we're not getting the exact values. All right, so this is just ordinary least squares regression, came down to these terms, 1.458 and 0.45, okay? If I were to just use the optim function, okay? So if, you did optim in your homework yet, or not yet? Maybe, okay. So anyway, here I'm going to just say, let's optimize the ordinary least squares loss, okay? And so ordinary least squares loss is going to return t minus xw transpose times t minus xw. And we say, all right, try to optimize this loss function. And if we optimize the loss function, it comes down to the same values, 1.458, 0.4533. Okay, and that makes sense because OLS is trying to minimize the mean squared error here, all right, or the total squared error. So that's what we have. Okay, so the loss function, again, just takes in W1 and W2, plugs it in, gets our loss function. What we're going to do is we are going to modify the loss function. Oh, this is the contours of the ordinary least squares loss function, and it looks like this. Okay, where the minimum occurs at 1.5.5. Okay, so this is the loss function. This is the contours of the loss function. This is where our minimum is. Or actually, this is not 1.5. This is the minimum at 1.458 and 0.4533. This is using the data that we have. These are the contours of the loss function. Okay, what we're doing now is I'm modifying the loss function. So we're going to create a new function called the L1 loss function. And this L1 loss function takes our observed data, our W1 and W2 values. It calculates the OLS loss. Okay, so it takes this earlier function that we had here that we've written that does T minus XW transpose T minus XW to get our loss function. It calculates that, plus it adds a penalty times lambda. Okay, and what is that penalty? The penalty is the sum of the absolute values of the coefficients W1 and W2. Is that okay? So we're going to take the coefficients W1 and W2, we're going to add that in, and this is our new loss function. And we're going to say, you know what? I want to minimize this loss function, okay? Whoops. Okay, well, I want to minimize this loss function. So the L1 loss, we're going to try to minimize this thing, okay? If we only cared about minimizing the L1 norm, okay? If we didn't care about minimizing ordinary least squares loss, then we would end up getting a thing that minimizes kind of it would try to fit the contours. The contours would be these diamonds, okay, centered at the origin. And effectively, we would end up picking eventually we would end up at the origin, where we shrink the W1 and W2 terms. But basically, the loss function we end up kind of is going to end up, if you think about how does this work, we end up it's going to end up hitting vertices here, and at the vertices, generally one of the variables, W1 or W2, will end up being 0. Okay, the actual loss function that we're trying to minimize includes both this L1 norm, lambda times the sum of the absolute values of your W coefficients, plus the OLS loss. Okay, and so we're going to end up getting kind of a loss function that's a bit of a hybrid between these two extremes. So this is OLS, this is L1 only, and this is these are the different coefficients that we get for different values of lambda. Okay, so here, if I say what are the coefficients for ordinary least squares loss, we have 1.458 and 0.453. If I put in a lambda of 10, okay, we're using optim, well, lambda equal to 10, these values shrink down a little bit. If I say lambda 50, they shrink down even more. If I say lambda 100, they shrink down even more. Okay, how much are they shrinking? They actually shrink by equal quantities. This one, 0.458 to 0.436, we're shrinking by around 0.22. Okay, and this one we're also shrinking by around 0.22. Okay, from 0.453 to 0.4306, we're shrinking by about the same quantity here. Okay, how much does it shrink from here to here? Okay, almost 0.1. How much does it shrink from here to here? Almost 0.1. How much does it shrink from here to here? We're shrinking both of the coefficients by the same amount. Okay, and as I increase my lambda even more to 180, 300, 500, okay, these values shrink even further, and they keep going, and this one until they both effectively become 0. Okay, let me just show you what happens. So here I'm drawing 0, 0. What this represents is what coefficients do we use for W1 and W2? So W1 is the coefficient for X1, W2 is the coefficient for X2. The true values are around 1.5, 0.5, and the OLS values are like 1.458 and 0.4533 or something like that. Okay? With lambda equal to 10, the regularized coefficients are at this blue dot, which is very close to the red dot. Okay? As I increase my lambda, the blue dot, the coefficients for W1 and W2 shrink a little bit more. Okay? This says the parameters are a little bit less. Okay? And as I increase lambda even further, the blue dot comes down further, and you can see it moving diagonally until it hits 0. Now W2 has been shrunk to 0. W1 has been shrunk to around 1. And then as I increase, W1 keeps shrinking until it reaches 0. Okay? And the contour lines also look funny, right? So here we start off with something that looks kind of like the ellipsoid contour lines. And then as I push the extreme over here, okay, as I increase lambda, we get these weird looking contour lines, right? These kind of look like straight lines, and then there's like this weird arch here, and it's what it is it's a blend between the two extremes of the diamonds and the ellipses, okay? And if you're trying to like morph one into the other, you're gonna get something that looks like this, okay? And why is the harsh bend right here at these lines 0, 0? It's because it's the absolute value. So if you think about the absolute value function, there's a harsh bend right at 0 as well. Oh my goodness, I've talked way too much. Okay, second view quiz answer is A. A as in apple. A as in apple. A as in apple. Okay, so here I wrote, as the lambda increases, the contour lines begin having sharp corners and straightish edges. The optimal parameters travel diagonally until it hits the x-axis. Okay, they travel diagonally until they hit an axis, and then it gets pulled into the origin. Okay, so increasing lambda will affect W1 and W2 equally, and that's why we see the diagonal movement. Okay, because it's shrinking W1 and W2 at the same rate until it can't shrink one of the variables anymore, and then it shrinks the other variable only. Okay, so the diagonal motion means both the slope and the intercept, or I guess technically the W1 and W2 parameters decrease by the same amount as lambda increases until they hit the 0. Okay, let's look at ridge regression. Same idea. We're taking the OLS loss, and then we're adding the coefficients W1 and W2. We're going to square them and add them in, okay, multiplied by lambda. Okay, and here are the numbers, and it's hard to see any kind of pattern with the numbers as I increase this, but let me just show you what's happening here. Okay, so here again, we start off, red represents the OLS optimal values. Here I've drawn this diagonal line where W1 is equal to W2. And notice what happens to this blue dot. It moves towards the blue dot, and then it moves towards the origin. Okay? And then if you look at the contour lines, we start off with ellipses, and then we get something that looks closer to like circles. Okay? So when you do ridge regression, you're doing W1 squared plus W2 squared, okay? Which is kind of like the formula of a circle, right? And so for LASSO, you had diamonds, absolute value of W1 and absolute value of W2, and if you plot those, you get kind of these diamonds. And if you look at W1 squared and W2 squared, the extreme would be, if you're only looking at W1 squared, W2 squared, you're going to get circles. And so the extreme on one end is we have these ellipses centered over here, and the other extreme are circles centered at the origin. And so this is kind of like the hybrid between these two. And so the summary slide just says as the lambda increases, the contours look less elliptical and more circular. And what we see is that the parameter values travel first towards this line where W1 is equal to W2. And the reason why is because if you think about the penalty applied to W1 squared and the penalty to W2 squared, if W1 squared is huge, like 100, its penalty becomes 100 squared, 10,000, okay? And if W2 is small, 1, and we square it, it's still 1. Or if it's less than 1, 0.1, and we square it, it becomes 0.01, okay? And so squaring things ends up penalizing very big coefficients and penalizing small coefficients very, very little, okay? And so, if we go from 11 to 10, that reduces the squared penalty from 121 to 100, while reducing from 3 to 2 will reduce the squared penalty from 9 to 4. So it's going to try to shrink the biggest coefficients first, because that's going to have the biggest impact on shrinking the squared penalty versus shrinking these smaller coefficients. Okay, so it shrinks the bigger ones first, and the consequence of shrinking the big one is it tries to kind of compensate by inflating some of the other ones. Okay. Let's see. I think I'm going to run out of time for this part, so we will. I don't know. Okay. Maybe I'll just kind of cover it quickly here, and then I can go over it briefly on Monday as well. Okay. The concept here is our observed data is random, okay? And so here, what I've done is I'm going to generate a bunch of different random samples from the population, right? And so even if you have the same underlying base model, if you observe different random observations, you might get different coefficients, right? And so so here, this represents the OLS thing. So the true parameters are 1.5 and 0.5, okay? But here I've generated 1,000 different data sets where I added random noise, okay? So I had 16 observations, and I said fit the model, and the very first time I did it, the model that I fit had best parameters of, what was it, 1.458 and 0.4533, okay? And that was just the effect of the randomness. Now, on some rare occasions, just because of the random noise, the coefficient that gets fit is going to be like 1.0, 0.8. Or maybe in some other cases, just by the random noise, we get coefficients of like 2.0, 0.1. Okay? Most of the time, they're around 1.5, 0.5, but sometimes because of random noise, we get something a little bit higher and a little bit lower. And so this cloud represents the variation of the different W1 and W2 parameters that we might estimate based on just random noise alone. Is that okay? Got 1 minute here. When you do the L1 penalties, when you apply lambda equal to 10 to this, it basically shifts all of your coefficients diagonally a little bit. And so you can see like the red dots are just like a shifting of the black dots, okay? And if you increase lambda even more, it shifts the entire thing even further. But what has happened is that because it's absolute value, it's never going to go into the other side. So when they hit the origin, they just kind of all shrink to 0, okay? And so as they move diagonally, they just kind of die at 0, okay? Right? They're not going to, like the cloud isn't going to go over here because that's going to increase the penalty over here. And so this thing ends up having less variation than this thing because this takes up less, the cloud is smaller here, okay? And so increasing kind of your lambda parameter, and if you increase your lambda too much, everything gets concentrated just down. It's hard to see, but all the dots are concentrated right at 0, 0, right? And there you have no variation there, okay? But that's just silly because why even bother? But using this basically shrinks your thing, okay? So this is kind of the illustration here. Something similar happens when you do ridge regression, except they tighten up into a smaller ball, okay? And so here, this is, the OLS ones are the black dots, and then it's kind of like imagine this on some kind of rubber thing, and you shrink this rubber until you get this kind of tighter and smaller cloud for different values of lambda here, okay? Anyway, we're out of time. Let me give you your last view quiz answer for today. Last view quiz answer is C. C as in cat. C as in cat is your last view quiz answer. Okay, we'll wrap it up here. Have a good weekend, and we'll see you on Monday, but online at 6 p.m. Okay, all right, we'll see you later.